present to us how VUnit and also other open source tools are used in a very, very large scale FPGA system.
Welcome everybody. I'm Alberto Perro, and I'm a PhD student at the LHCb experiment at CERN. And we'll talk today on how we planned and how we executed the modernization of our validation and verification frameworks for our Gateware in the LHCb experiment. So just to give you a brief overview, first introduce our experiment at CERN. Then I will dive a bit more into our current situation regarding the Gateware and the FPGAs, the motivation that moved us to a more modern system, how we implemented the validation and verification, and how this works in our continuous integration, and in the end, a bit overview, very small overview of our common core library, which will use all of these other tools. So just to start, and for everybody who doesn't know what CERN is the European Organization for Nuclear Research, and it's the world's largest center for particle physics studies. And the Large Hadron Collider is the largest accelerator complex with a circumference of 27 kilometers, and it's placed 100 meters underground between the border of France and Switzerland. And the LHC hosts 4 major experiments, which are Atlas, Alice, CMS, and in the end, LHCb. The LHCb experiment is a very specialized experiment which investigates the differences between matter and antimatter, studying specifically the beauty quark. The study of short-lived particle and rare processes is done by looking at the particle going forward in one direction with respect to the collision point. And the LHCb collaboration is composed of over 1,700 members from 22 different countries. So just a brief detail on the physics. I will not give you a physics lesson today, but the basic of particle physics right now is that we need to collect a sufficient amount of events, which for us is collisions that are interesting, and perform the physics analysis. And in particular, the rare processes that are searched in LHCb require collecting huge amounts of collision events. Collisions happen 40 million times per second in our accelerators, and then filtering them to get the interesting events out. So just to give you some numbers, these are basically what we call branching ratios, which are the probabilities of that kind of event happening. And this is in 7 years of run taking, between run 1 and 2, from 2009 to 2018. And for example, you can see that the last row, in 7 years, we got only around 208 events. Okay, so here is the LHCb experiment, and this is a cross-section of the experiment. As all of the physics experiments is sort of built in a specific way that has a tracking system to track the trajectory of the particles, and a part that does the particle identification, and then calorimetry. I will not go too much into details, but the difference between LHCb and the other experiments is the fact that the collision point is not at the center, and it's all to one side, on this side, because we look only in the forward direction. So from here, the particle will go only to this direction, and we look at them specifically because this is the region that our interesting events are more likely to be. As I said, we have a tracking system. The tracking system is composed of 3 stations. The first one is the vertex locator, then the upstream tracker and the sci-fi tracker. These are made both from pixel CMOS technologies and from, in the case of scintillating fibers, the sci-fi tracker is scintillating fibers. And what they do is just they track the position of the particle that is crossing them, and this gives us first information on the trajectory, and thanks to the magnet here, we can extrapolate the curvature of the trajectory, and then since Lorentz law, we can reconstruct also the momentum of the particle. Another part that is very interesting that uses a special, not so known effect is the Cherenkov detectors, which are these rich stations. And this particular effect, I will not explain into detail, but basically can give us information on the velocity of the particle, and together with the information of the tracking, we can also identify which kind of particle we are dealing with. These are all non-destructive measurements, and in the end we have destructive measurements made by the calorimetry. So basically particles will just go through this calorimetry station, and these are just made by an absorber layer, and so the particle will be absorbed, and we look what is the distance that they penetrated through to get how much energy they had. In the end, in the green part, the only surviving particles are neutrinos and muons, but neutrinos, they don't interact very much, so we don't care about them, and we just look at the muons. This is very useful information for how we want to look at events and how to filter them. So how do we get data out from all of this very complex system? In the previous slide, I can show that this is 20 meters wide and 10 meters tall. It's around 6,000 tons, if I remember correctly. So it's a very big experiment. So to get all of the data out from all of these different detectors that are in a radiation environment, and they are placed 100 meters on the ground, we have 11,000 fibers, which are speaking a particular protocol that is developed at CERN, and it's radiation hard, which is called GBT. All of these 11,000 links are connected, they are brought to the surface, where we have our data acquisition cluster. The data acquisition cluster is made of FPGA cards, which are reading all of these fibers, and the event builder servers, which is where our FPGA cards are placed in, and so they pass the data from the fibers through PCI Express to these servers. The server then will build the event, putting together all of the fragments, which are our puzzle, and this is done on a network that is capable of 32 terabit per second performance, and this is using InfiniBand. Then on the same servers we do our first filtering, which is done on GPUs, all in software, and after this first filtering we get the throughput down to 1 terabit. Then there is a small buffer store, smallish buffer storage is around 50 petabytes, and then after this we have HLT2, which is our second filter, and after this we can write to tape our events for later analysis. So let's focus back on the FPGAs. Our current situation is that we have a custom board, which is called the PCI 40 here in the picture, and it's quite beefy board. It's 1.2 million logic elements from Intel Area 10. Is capable of dealing with 48 of these specific custom links at around 5 gigabit per second. It has also 2 SFP plus modules to deal with the clock and timing requirements of all of the experiments, and also the PCI Express interface. We employ 520 cards in the all experiments, and this is subdivided in 3 flavors. The readout supervisor, which is the master that controls the end. Well, it transmits the clock of the collisions, and it distributes the real-time control commands. Then we have the control plane, which is the interface to the front end, and this deals with the slow and fast controls. So, for example, setting power supplies and various settings in the detector itself, electronics. And then in the end, the most important part is the data plane, which is called L40, and it acquires the data from the front end, processes it in a bit, and then delivers it to the host through the PCI interface. So this PCI 40 has also a gateware, obviously, and this is also built as a common platform, since the PCI 40 is a common platform. And we offer common RTL blocks, which are shared between the subdetectors to reduce the development overhead. And then the subdetectors, so the different part of our detector system, have to develop their own specific RTL blocks to process the data format and maybe do also some other more complex processing before sending the data to the event builder. And this results in more than 30 different gateware variants to test and to maintain. So what is the current situation of test and maintenance? Well, unfortunately, the test coverage is very limited, and the test benches can cover only a small amount of cases that are very tailored by both subdetector people and the main people to just test that it sort of works. And as also Tiago said, this was the old approach. Is all based on custom TCL scripting, and can only run in one simulator, and sometimes it's even like version tied, which is very bad. And also, this simulation will take a lot of time. Almost 3 hours for a single gateware, so you multiply with 30, it's a lot of time. And we cannot run them in parallel because each of the instances of simulators require a license, and CERN has a very limited pool of licenses. So what we wanted to do was to start an effort to use modern validation and verification methodologies in our gateware development, because we need better and more exhaustive integrated testing. We also want to get rid of all of the proprietary code, because vendor libraries are limiting our selection on both test tools and the portability to a new platform. And also, we have a lot of developers developing basically the same thing, and this will just hide corner case bugs everywhere. More important, we also want to upgrade our data acquisition system. We will increase our total throughput by 6 times in the next run, so start of 2028. And this requires a new platform as well. Our platform is not capable of doing it, so we are designing the PCI 400, which is a new beefy board, always from Altera, based on the Agilex 7. And even though it's the same FPGA vendor, this requires a major porting effort due to the transceivers being different and all of the actual FPGA stuff being different. So having a complete and integrated validation and verification will become crucially important for us, because also the increase of complexity in Gateware, since this new FPGA will be around 3 million logic elements, so quite big. So how we approach the different angles of the validation and verification? Well, we started with automating testing of the whole DAQ gateware through precise and complete test benches, the use of a common library called Colibri, which is both verified, validated, and vendor independent, and also functional and formal verification, where possible, of common and custom RTL modules. We used VUnit for our full gateware test benches, because this helped us to maintain and automate the tests. Custom TCL scripts were completely replaced by a very intuitive Python-based interface, And since our current simulation used some HDL packages, VHDL packages to configure the different simulations, we just use the old code that we used to modify this by calling the pre-simulation, using the pre-simulation hooks in VUnit. This was very, very easy to do. It took like some day to port all of this into VUnit. Also, the output of the simulation is right now checked by an external checker. So the simulation will write to a file, and so we can run this external checker and integrate it into VUnit seamlessly by calling the post-simulation hooks. Also, as already mentioned, before we couldn't just run a finite number of simulation in parallel because of the licenses, and VUnit made this very easy since its capability of integrating with different simulators helped us porting the test benches between the different vendor tools. And with this solution, we ported the different test benches to both NVC and GHDL. And these open source VHDL simulators are without a license, obviously, so they're very easy to use in CI. And this enables us to improve our CI just running multiple test benches in parallel. Also, we still use fast and proprietary simulators. They are obviously faster than the open source ones, but just for developing. But this is very easy just to change with an environmental variable in VUnit. On the other side, we developed a common core library, which is just a collection of the most common cores we use and we've seen being used by our developers. This has been written in a subset of the HDL 2008 that has been tested with most of the tools we use and even other vendors' tools. And this library is open source and is going to be available probably at the end of the year under the CERN Open Hardware License with repository. And the modern testing methodologies that I have presented were built into the library core from the beginning. So we have test benches, we have formal verification, and even more for each of these components. And obviously using VUnit was the main element to do these testing pipelines in unison with the verification components as OSVVM and VUvm. So the features that we think are the most common and important of VUnit that we used is the functional models or verification components, which are not as complete as the OSVVM and VUvm ones, so in some cases we have to go and use those, but they are very easy to use and cover most of the applications we need. Then the configurations, so expressing different configurations via generics is extremely versatile for us. So for example, if we have a protocol that needs to sweep over a bit width or number of lanes, for example, we can just deal with this into VUnit and then run parallel tests on all of the different configurations at once. The other important part is the reports, which are in a format that can be integrated in the pipelines, simplifying the bug catching and early debug during development phases. And also the communication, which we used a lot to develop very complex test cases because the communication can handle different processes, even in different entities, so this is very useful. Other open source tools that are part of our toolset and workflow is the tools for formal verification. So for the people who's not aware for this, is just a set of techniques that use basic static analysis to determine the correctness of gateware behavior. And this can guarantee the absence of bugs since it's a mathematical proof. A model satisfies the requirements. So components that can be formally proven. There are some limitations to this tool. Are already equipped with the formal verification test, and also the formal verification helped us debug some very nasty corner case bugs in our gatewares that is currently running. So the full workflow is also implemented in CI, uses GHDL, IOSIS, and symbiosis. Last but not least, the coding is the most important step to make the code readable and understandable by developers. So in our collaboration, which is quite big, and we have developers from very different backgrounds, from electronic engineers to physicists to mathematicians and more, it's essential to have a common style to speed up both code review and code integration. Coding style is enforced by another open source tool, which is called the VHDL Style Guide. It's enforced in the CI. And also we have documentation that is managed by, well, first well-commented code, and the integrations with tools like Terra's HDL and Wavetron. So to conclude, the work presented was to show how the integration of the modern methodologies could be beneficial and speed up gateware development, and the structure of the project, and allows the easy adoption, portability, integration in both current and future gateware environments. The open source tools were crucial to develop this system, this infrastructure with the limited manpower available. And of all of the tools, I would spend a word on VUnit being the most important element in the whole project, and the one that brought the most tangible benefits, specifically thanks to the multi-simulator support. And VUnit was successfully integrated in the current Gateware as a pilot project to evaluate these modern tools. But from the successful results we saw, we see that in the upcoming PCI 400 project, we will heavily rely on VUnit and the other methodologies presented here. Thank you.
Yes. Hi. How do you handle the fact that obviously in a project like this you will have big proprietary IPs? I imagine like MGTs or like in Xilinx there is a thing called the NOC, or things that it's really difficult to simulate. You just do not simulate, or there's some workarounds?
So in our case, we don't have a NOC, and most of the code, well, all of the code base is written in VHDL, and for the IPs, we can integrate directly the IPs, generate, for example, we use QSys, which is the IP builder for Altera, and it can generate a simulation model, and then we can import that into VUnit. That could be a limitation only in the case of the tools that you can use, because, for example, this QSys generated stuff is encrypted, so you need a simulator that can decrypt, and that is Questa with the Intel license, or Riviera with the decryption stuff, but not open source tools. That's the only limitation. But for most of the stuff that we need, which is a bit higher level than transceivers, we can just do without having to resort on any of this.
I have a question on top of it. I was going to ask, how do you deal with the multi-language situations? I had strictly in mind the transceivers with parallel code, but obviously you just split it out. So you focus on your code to be written in VHDL, and you specifically just test or simulate that part with open source simulators, and then you integrate with the IPs, and you don't simulate the combination with the system code, something like that.
Yes, exactly. So most of the, well, let's say IP stuff, it has been, well, we in our case we don't develop the low level, so transceiver stuff. We use something that is given to us by other departments inside of CERN, So we assume that as test set, we just integrate it, but we only, well, the only part that we care very much about is the full simulation of the data flow, not the endpoints, let's say. So this is the biggest work that we have to do. On the side of multi-language support, we don't use it. Like, we are required to use VHDL for most of the stuff that we have. Sometimes happened that we had some system verilog. Again, with VUnit it's very easy to import, and but this will just limit the tools that you can use, but not the framework itself.
Thank you.
I can add something about the mixed language environment. So in the project I'm sitting in right now, the solution we have is that, like Thiago mentioned, we are very much unit testing based. So our testing is like something called test pyramid. Very many unit testing, and then integration testing and system testing becomes fewer and fewer. And typically, all those very long IPs comes in at the high levels. So 90+% of our tests can run in GHDL or MVC in parallel threads. What we use there is that we use the dependency check in our VUnit. It's not public interfaces, but it's possible to figure out what tests depend on Perro. And those will be run only in Questa in that case, but every other test will automatically be found and simulated in one of the open source simulators. So that's a way to automatically separate what depends on Perro and what doesn't. Any other questions? No. So thanks again, Alberto.